In this section, what we're going to do is look at extreme forces and basically the effects that occur on buildings from earthquakes, wind, fire, and blast. First, we want to look at earthquakes, and we'll take a look at some of the basics. Again, this is just an overview for you. You're not going to come out being seismologists. But how much damage are we going to get from an earthquake? Well, it's going to be determined by several things. One, the type and degree of shaking that occurs at the site, and also it's going to be determined by how the building or the structure responds to that shaking. Different earthquakes will cause different ground movements or shaking. For example, earthquake, if the site is next to the epicenter earthquake, the shaking will be very quick, high frequency, and what will happen is this will affect the shorter, stiffer structures more than the longer or taller, more flexible structures. Further away, where you get the dampening out of the high frequency shaking, you get instead the longer amplitude or longer period shaking, and there you see damage more to the taller structures, those that are more flexible. The thing to remember is that not all structures are going to be affected the same from a given earthquake. Again, you know that we use a magnitude number to determine the severity of earthquake. That magnitude 7, magnitude 8, corresponds to the amount of energy that gets released during the earthquake. For us, that magnitude, the higher the number, is going to determine the potential number of affected structures. Certainly, we're not going to think that much of a magnitude 5 earthquake, but when we get up to magnitude or over magnitude 6, you get into the 7s, well then you know you're going to have a lot of damage. Another thing to keep in mind with this number is that it is not a simple arithmetic or linear scale. It turns out that as we go from, say, a magnitude 6 to a magnitude 7, we actually have approximately a 32 time increase in the amount of energy released. Now, for us, a big problem with earthquakes is the aftershocks. And this is somewhat unique to a disaster in that even though we'll sustain heavy damage from the initial quake, we as USAR personnel need to keep in mind that certainly aftershocks are a given, and that even though, as we'll see, that the aftershocks are almost always going to be smaller in magnitude, now what happens is that they'll be acting on a damaged structure. So even though a structure survives the initial shock, it certainly can have the potential to collapse during an aftershock. How many aftershocks? Not easily predicted. There are rules of thumb, one from the USGS that said that for every single decrease in magnitude, it's going to be about a 10-fold increase in the number of aftershocks. And you can see an example for a magnitude 7. And what you find is that as the days pass from the initial quake, that you end up having fewer and fewer aftershocks, and typically the magnitude also goes down. And this is just an example from the 1989 Loma Prieta earthquake and the amount of aftershocks that occurred. The original quake was about a 7.1, and you could notice that almost right after that there was a 5.2, 5.3, rather significant. Again, quite a bit smaller, but then again acting on damaged structures. And note, again, this, we're not going to be there for the initial quake. We're here afterwards, and again, subject to these aftershocks. Now, why do we get loading on the structures, on the buildings from earthquakes? The loading occurs is actually an effect of the ground motion resulting from the earthquake, mainly due to the weight or the mass of the structure. Turns out that the heavier the structure, the higher the forces. The higher the forces will get on the structure during the earthquake. A good analogy would be if you're sitting as a passenger in a car and the driver punches the accelerator, what you're going to find is that you can feel the force as you get forced back into the seat. If the driver then suddenly slams on the brake, again, you're going to feel that force as you try to move forward against the seatbelt, or if you're not wearing the seatbelt, you'll feel it against or feel the dashboard hitting you. Again, it's that inertia of the mass. Now, because again the force is related to mass, to weight, what we find is that it's the heavier buildings that sustain the higher forces during an earthquake and then typically see the greater damage. Again, we talk about the URM, or the unreinforced masonry structures, being real weak. They sustain heavy damage. And again, they have basically two things going against them. One is their mass, their weight, plus the fact that basically a very brittle structure. We even get damage to under or unengineered wood structures. Again, if they're not properly constructed for earthquake or seismic conditions, they will get damaged. Typically, we don't see collapse, but again, in the end, they become uninhabitable. What the first example you see is a wood frame that has been stuccoed with good sheathing. Did not collapse. Again, probability of anybody being in there is injured, trapped is quite low. It's interesting to note that that portico sustained the most damage. One problem there is that is almost like an attachment that doesn't get properly constructed or connected back into the main portion of the building. The second photograph is a wood frame structure, but with a brick veneer. The problem with the brick veneer, it's non-structural, but what it is doing is adding weight to the structure, and it was actually the weight or mass of the brick that caused the damaging forces to develop in that structure. One thing to remember is that it may not only be the collapse or partial collapse of the structure itself that can entrap victims, but it can also be the contents of the structure. And one example is shelving or storage racks. I always joke the one place you don't want to be during an earthquake in California is a home improvement home or a store such as Home Depot. Especially don't go be looking at riding motors during an earthquake, because they tend to store some of those up at the top shelf of the rack. We'll now look at wind loading. Again, wind loading comes from the movement of the air. The forces that get applied to the structure include a positive force or pressure on the windward side, but with wind, what you have to realize that there's also negative pressure or a vacuum that can develop, and we see that on the leeward side, and more importantly, on the roofs. The roofs actually get subjected to an uplift force. And here, unlike earthquake loading, where there the weight hurts us, here with wind the weight helps us, because we find that helps counteract these negative pressures or forces. Now, where do we get the wind? Well, obviously one would be hurricanes. There we have winds from it could be from 73, 75 miles an hour up to 175 miles an hour. Now with that, what you have to realize that the force that develops from wind is proportional to the speed squared. meaning that if you have a 100-mile-an-hour wind, that is going to be a force that is 4 times that you would get from a 50-mile-an-hour wind. Again, so when you go from a Category 1 to a Category 5, you're getting a very large increase in the damage that is possible. Now, again, we talked about the fact that weight with wind helps you. And what we find is that we get a lot of damage to the light structures, the wood frame houses, light metal buildings. Another problem with the wind is that you end up with airborne missiles that upon impact will cause damage to the structure. Sometimes what they do is that they compromise the exterior shell of the structure. This allows then the wind to get inside the structure, which will then quite often blow apart the building. With the hurricanes, we get the storm surge, and again, there we have forces being developed through moving water. Water, the types of forces that we get on structures from water is similar to wind, except they're more devastating because the forces are much higher because the mass of the water is far greater than the mass of the air. Again, other examples of damage from storm surge or moving water. Tornadoes, though typically more localized than hurricanes, their wind speeds are much higher, up to and sometimes exceeding 250 miles per hour. So again, the forces are much greater. Another problem with tornadoes is that unlike hurricanes, there's very little advance warning. Consequently, you have potential for more casualties. One devastating tornado occurred in and around Oklahoma City in 1999. Here it was an F5, or one of the highest categories for tornadoes, and also had a very wide path, up to a mile wide path. Much devastation. We want to turn our attention towards blast effects. There, with blasts, what you end up with is a very rapid release of energy. You get that bang, but you also get heat and light or a fireball. The pressure wave, even though it is very short duration, and it's actually an increase in pressure, that pressure is very high. Whereas for wind, we only see pressures of about less than 1 pound per square inch. With a blast, you can get up to about 5,000 pounds per square inch. The shock waves are actually pressure waves, and they'll propagate radially out in all directions from the source of the blast. And it's this pressure wave that causes most of the damage to structures. Blast is kind of like horseshoes. Distance is everything. And the further away you get, the less damage that you're going to see. But you got to worry about problems where the pressure wave can get amplified or combined due to it bouncing off the ground or other structures. The fact that the pressure wave is of short term, maybe a millisecond, this actually allows some structures to survive this very high load versus a load of the same magnitude being put on for a longer period of time. Some other effects with blasts is the high speed of winds that we get from the sucking action that occurs as the pressure wave passes. And again, you can also get ground shaking from the high intensity of the blast. What can be particularly devastating to a building is an interior explosion. There, you contain that pressure wave, it builds up, and will affect all immediate components of the structure. Typically, what we can do is in buildings, typically we can tolerate the loss of a floor system. It's much harder to tolerate the loss of the column. Again, the column is what's actually carrying a greater portion of the load down to the foundation. Just a schematic of an exterior explosion. Again, all things being equal, the pressure dissipates a lot faster in an exterior explosion. Again, here distance is everything. In addition to the positive pressure at the face of the building, what you find is that you do get pressures on the top, an overpressure, plus pressures on the backside as well as the sides from the drag of the pressure wave going across or over the building. Here what we're going to see is a video clip of a explosion that occurred at a rocket fuel. This is particularly interesting in that what you need to do is notice the building in the back of the blast. This is actually, ironically, a marshmallow plant. But as you see this video in slow motion, you can actually see the pressure wave go over the top of this building, and you can see the roof system ripple as it passes by. Fire. Certainly talk more about this since 9/11. Fire and the heat resulting from fire affects the structure, affects the material, particularly steel. What effects do we get? One is expansion. Steel and concrete will expand about 10 inches in 100 feet when the temperature goes from ambient up to about 1100 degrees Fahrenheit. Just to put that in proportion, the World Trade Center was about, I think the side dimension was about 200 feet. So, bringing the steel up to 1100 degrees would have caused up to a 20-inch expansion. In addition to expansion, we get loss of flexural rigidity, meaning that the steel becomes more flexible. What you find is that the beams will deflect more and begin to drape, and this can add additional forces on the columns. We see this loss of rigidity at temperatures above 800 degrees Fahrenheit. Again, the fact that the temperature is increasing, warning sign would be increased deflection in the floor. Once we get above 1,000 degrees Fahrenheit, then we actually get a loss in strength of steel. And again, what this will do is it will allow the members to fail. And most significantly is that eventually the columns lose stiffness, lose their strength, and then they buckle out. And so schematically, this just shows the effect that an expansion might have on a structure. Again, the floor system, which traps the heat underneath, will expand and deflect the columns out. And again, this obviously would weaken the columns and make them more susceptible to buckling. As the temperature increases further, we lose the rigidity in the steel in the member. They sag, and now what they're doing is the floor system is pulling in the columns, again, helping to destabilize them. Again, you see a floor system like this, you're inside, you don't want to be in there, you need to get out because it is a warning sign of impending collapse. Here, at some point, you're going to lose the strength in the floor system. It collapses. The problem here is we now have columns that were supported at every floor. Now they're unsupported over a greater length and, again, more susceptible to buckling. And basically, this is one of the contributions of collapse of the World Trade Center towers. Again, what are the effects of fire? Again, strength loss. The greatest effect is on horizontal members, the joist, beams, and columns, because the heat gets trapped under the ceilings. Plus, we find that the smaller members with high surface area to cross-sectional area collapse first, just because they heat up quicker and lose their strength. The larger, thicker members in the building take longer to get up to critical temperatures. So you see less effect on columns, again, because the heat is getting trapped up only up at the upper portions of the columns. They're also, the columns are typically thicker members, and they actually can dissipate the heat to floors or column sections both above and below the affected floors. Now, in wood structures, the thing to worry about is that the wood members can burn out, and this can leave, say, exterior bearing walls unsupported and then susceptible to collapse or buckling. Example of this was the Worcester fire up in Massachusetts in 1999, where the wood interior burned out, and this left the exterior unreinforced masonry walls unbraced. And during the recovery operation for the 6 firemen that were trapped in there, the structure specialists had to continuously monitor these walls because now they were susceptible to collapse from say, high winds. The manual that you have access to does talk about additional effects from floods, tidal surges, tsunamis, landslides, mudslides. Also, the problem with construction bracing, or really the lack of bracing during construction, where you get collapse. Also overloads and vehicle impact loading. So at your leisure, you ought to look through that. And again, these are just more effects that can cause overloads on our structures or buildings.